Sukla and co-chair Engineer Anna Ponni. I would like to request Dr. Jayakumar Sukla, our chairperson, and co-chair Engineer Anna Ponni to invite our thematic speaker, S. Banerjee, to share his valuable insight with us. Over to you, Dr. Shukla.
Very warm welcome to everybody after lunch. It is too difficult after lunch. The session is, our session is earthquake and soil dynamics, and we have our very eminent speaker as a theme speaker with us. Professor Subhadeep Banerjee is going to present on the title called Towards a Practical-Based Approach for Simplified Liquefaction Susceptibility Assessment. I will introduce Professor Subhadeep Banerjee. Professor Subhadeep Banerjee is a faculty member in Department of Civil Engineering at IIT Madras. With a PhD from National University of Singapore, he specializes in seismic foundation interactions, cyclic behavior of geomaterials, and modeling of transient problems. At IIT Madras, he leads 3 research groups exploring cyclic characterization of soils, constitutive modeling under seismic loads, and dynamic applications to complex soil structure problems. His works contribute significantly to advancing the geotechnical engineering practices and understanding soil behavior under various dynamic applications. With this, I would request Professor Banerjee to have a theme session on towards a practical-based approach for simplified liquefaction susceptibility assessment. Yeah.
Thank you, Mr. Chairman and Co-Chairman. First, I thank the organizers to giving me this opportunity to talk some initial work which we are doing on particle-based approach of the liquefaction. Now, let us start with some basic understanding of liquefaction, which all of you are definitely aware of. We all know that under condition, under fully saturated situation, cohesionless soil will have this excess pore pressure build-up problem, which will cause the loss in contact among the particles, and then trigger to the flow behavior, which is we nicely term technically as liquefaction. Now, what are the factors? See, there are different groups commented on different governing factors. If we class that, it will be like different types of earthquake characteristics, site characteristics, and the soil characteristics. Now, here, for soil characteristics, for a clean sand particle shape, gradation, relative density plays a major role. So this is all we are aware of from the literature. Now, let us take a look at this one. See, ultimately, it depends on the soil strength or strength against the liquefaction. And we all know that relative density, there is no rocket science. If you have a better relative density, you will get the more cyclic resistance ratio. So there is a less chance of liquefaction. Same thing, if you have a higher coefficient of uniformity, that means you have varied sizes of particles, so you have good interlocking, which will cause higher cyclic resistance. But the problem here is, if you see that particular, the right one graph, for same coefficient of uniformity, one guy is showing cyclic resistance ratio of 0.1, and another triangle, that uppermost triangle, is showing close to 0.4. Now, that means, what I'm trying to say here is that these factors, can they be independent or they are interrelated? Now, even more interesting thing is, now people go for the morphological characteristics, and then there are 3 morphological parameters, actually 2 parameters, roundness and the sphericity of the particles, which we club into one as the average of that in regularity, which basically, forget about the numbers, because post-launch, these equations are not good for health. So what I'm trying to say is, if you have a good regularity, higher regularity means you have more rounded particles. More rounded particles, we all know, the interlocking is less, so you will have the lower resistance to liquefaction. If you see the rightmost, the graph, it's all the data points are taken from all over the places in the literature. If you see overall, I can say that if the regularity increases, there is a pattern expected that cyclic resistance is reducing. But how much it is reducing? It's widely varied. You see, it's starting from the cyclic resistance ratio 0.5 to 0.1 for same regularity. So again, I reiterate the same question. Are these independent? Now, that's why the answer is, of course, no. And then let us introduce a new terminology called packing index. Now, what is packing index? We just trying to club these morphological characteristics with some macro parameters with that. So it's basically what we are trying to do here is, we are combining the uniformity coefficient, relative density, and regularity and together. So simplistic term, if you know the SPTN value, which I expect everybody is having from the soil investigation report, then based on the proposed method, you should be able to work out what is your angle of internal friction. And then from angle of internal friction, you should be able to work out what should be your phi alpha value, that means packing index. And then packing index, use this chart, or you can use this equation straight away to come up with CRR. Now, this all looks fine, but we have to validate, right? How good these are in the prediction with the traditional Idris-Bollinger concepts or Ewood's concepts, which are very well established in the design. And if you see from the present study, we compare a lot. I mean, varying years, starting from PEC's 1974 to recent ones. But if you see that if I calculate the mean absolute percentage error, then we are not too bad. In fact, we are better than the most of the cases. If we consider the Idris, Bollinger, and the Wood, they are the pioneers, and their methods are the most acceptable one, we are not too far off from what we propose. Now, this is the overall concept of the packing index. Now, for further detail, there will be one more follow-up presentation to this for the packing index in the Friday afternoon in the same earthquake engineering panel. There you can go for the further detail. What I wanted to highlight here is why this packing index, or how this packing index is important, from how to relate that macro to micro behavior. That's what we want to do a little more going deep inside. We try to do some discrete element simulation. So this is an ongoing work. I'm just giving you some glimpse of what we are currently doing at IIT Madras in terms of the discrete element simulations. My colleague here is there, my colleague Professor Ramesh Kannan, and my student Mujib, they are here. So they are the co-authors of this work. Now if you see, we start with a simple biaxial 2D simulations. It is 50 by 100 type of standard thing. It's 2D, it's still 2D. We are not venturing 3D yet. Just to try to see how 2D works. And if we try to match the percentage final. So this part, we just wanted to see that how the discrete element been able to replicate exact conditions of the uniformly graded soil published literature. So the literature which we use is the Nagy's recent paper on the similar line. And if you see, the Nagy's one also in a numerical exercise. And if we see that our initial, just a very crude validation shows quite a standard dense and loose behavior. I mean, standard dense and loose behavior, everybody aware that dense will have the typical strength softening and this one is a strength hardening behavior. Now, with that, we'll go for the, I have how many minutes? Another, okay, fine. So, then we went for a numerical exercise with varying the drainage conditions to extreme condition, drained and undrained, in loose and dense for the different confining stresses. Again, if you see, that's what I wanted to see, whether we want to see, whether we should go little inside. Now, I want your attention to the red lines. If you see in the loose sand, in the red line, what it shows, there is a quick, sharp jump with the shearing, and then followed by a very flat type of situation. So it's basically the strain is increasing without increasing of the levator stress. Shows that this is the kind of a flow behavior. And beyond 10% strain, there is again dilating nature is coming because it's a reorientation happened. So it's a kind of a post within bracket liquefaction type of situation where you are getting again the denser configuration coming back. Dense part, I am not going into detail because dense part is more or less established. It's not that important in this. So now with this macro behavior, let us go deep little inside with a micro response. Now, first one is a contact force anisotropy. So those who are familiar with contact force, they know what it is. But those who are not familiar, it is like you have 4 students, you gave a problem, there will be, with the pressure of the problem, three students will be immediately joined together, will leave one outside. So that means under stress, there will be a directional nature of the particles orientation, which in the hindsight, in the macro behavior hindsight, this will be the one of the reason why the shear band formation happens in the sandy soil. So same thing, for loose assemblies, the discrete element simulation shows that there is an increasing, gradual increasing of the anisotropy, and then followed by more or less stabilizes or more or slightly decreases, showing that beyond certain strain, again, it's like a post-liquefied dilation behavior coming to the picture. Whereas in dense sand case, you will see a very sharp increase in the anisotropy, and then beyond that, it's lost its stabilized configuration, become dilated, and its anisotropic behavior reduces. Same thing if you go to the coordination number. So forget about what is more mechanical coordination number. Let us see that this is a quantity which tells you how much the particles are interconnected with each other. I'm not going into the details of the mathematics of coordination number. Now, there is an optimum number of coordination number is required for different, for 2D there is something, people say it is 3, but there are studies says that it can be varied from 3 also. But let's say undrained behavior, again, drain I am not too interested for liquefaction. For undrained behavior, if you see, it is always coming down below 3 initially, and beyond certain level of the strain, 10%, again it is increasing. Again, why I am saying this, all this thing relates to your macro behavior, that it is liquefying followed by a post-liquefaction densification behavior comes into the picture. Dense sand, of course, there is a loosening up because of the dilation, but overall stability is assured at these particular cases, considering 3 is the optimum coordination number. Now, this one is, people wonder why there is a clear peak observed in the dense sand behavior. Now, there is one of the reason is, if you see that this is a X-shaped failure band appears, that's X-shaped. It clearly shows that X-shaped low displacement zones. It's a very localized, narrow zones in the dense sand appears. Of course, the red zones shows higher deformation because we are deforming from the top and the bottom. So, of course, we expect that. So, this may be the one of the reason why we get clear peak. Whereas loose samples, you will have more of a distributed deformation, the stresses. It's not so much of the concentrated. So, there will be no obvious peaks. So, final slide that this will show that some loose behavior, this is the final thing. So if you see the force chain approach, if you increase the strain from left to right, you will see that if I want your attention to the blue colors. Blue colors means loose contact. If you see from the leftmost to the right, you see the number of blue color chains, which are the weak force chains, is increasing. That means getting loosened up. The particle-particle contact is getting loosened up. And then again, at higher strain, the 20% strain, again it is coming back to the original because it is already post-limited liquefaction behavior, it's getting densified. So weakened stability, so this is what limited liquefaction, I say. For more details, of course, you can refer to this paper for detailed understanding. You can write to us, one of us, and then we'll further discuss. So I'll just conclude with a couple of slides. Please wait for the updates on this. So we'll be approaching for a very important project where Sumit is also there from IIT Delhi. So this is a multi-IIT project on pilot project on liquefaction susceptibility of the Gujarat region. So please wait for updates in our LinkedIn pages. And then finally, I take this opportunity to welcome all of you to IGC 2026 in Chennai. We yet to start the proper list of keynote speakers and other thing. Of course, it will be very interesting and interactive. Please come and visit us. Thank you.
Thank you, Professor Shubhadeep. We have one or two questions. If anybody has something to share or a question or a concern, probably we can. Okay, that means your session went very well. Everybody understood. Yeah, post lunch. Okay. Thank you very much, Professor Shubhadeep. On behalf of organizers, we would like to present you a memento.
So now we go ahead with the contributed presentation. So we have the first presentation, Cyclic Response of Soft Cohesive Soil. Authors are Shweta Datta and Ajanta Sachin. Please come over for your presentation. So you can take 6 to 7 minutes and 1 minute to wind up.
Good afternoon, one and all present over here. I am Shweta Datta, and today I will be presenting on the topic cyclic response of soft cohesive soil. The authors are me, Shweta Datta, and Ajanta ma'am. We are from IIT Gandhinagar. So basically we know that the dynamic loading are of two types, like high amplitude, low frequency, or low amplitude, high frequency. And in this high amplitude, low frequency, there are earthquakes or blasts, and in low amplitude, high frequency, there is like traffic loading, vibration, machine vibrations, wave loading, etc. But in this study, we basically looked the earthquake response of soft cohesive soils. There are, when talking about earthquakes, there are various seismic risk factors for structural damages. And from the past earthquake records, it has been seen that there are the different risk factors are poor structural design and construction, existing damages from the previous earthquakes already, some resonance amplification, and one of the important thing is the challenging foundation soil conditions. Challenging soil conditions, it can be soft clays or any kind of soft soils, because we know that it has higher compressibility, lower shear strength, and so. And unlike the cohesionless soils, which causes liquefaction, the clays or soft cohesive soils are known to cause cyclic softening or cyclic instability. So in this study, we have collected palette soil from Gujarat, and it has been made using the specimens were prepared using moist stamping method. In the weight of optimum, it was compacted at an OMC of at a water content of OMC plus 4%. The OMC was 11%, and we prepared the specimens at 15%. So the unconfined compressive strength of that specimen came out to be 39 kPa, which we say it falls within the range of the soft consistency. The specimens' two-way strain-controlled cyclic triaxial tests were performed, and the saturation process was done in 3 stages: CO2 flushing, water flushing, and force saturation. It achieved a B value of 0.95 at cell pressure 370 and back pressure 350. After that, it was consolidated at 100 kPa, and it was sheared under undrained boundary condition at 4 different cyclic strain amplitudes to see the variation of amplitude in this study only. And the tests were conducted at 0.5 Hertz loading frequency to see small seismic events. This is the hysteresis behavior of the soft cohesive soil. It has been seen that the peak cyclic stress was mobilized in the first loading cycle. It could be due to the strain rate effect, which is already mentioned in some previous papers as well. And a 2.35-fold rise in sigma D max has been observed for a rise in strain amplitude from 0.1 to 1.5%. The pore pressure response was evaluated for this soft cohesive soil in terms of both maximum pore pressure ratio and the residual pore water pressure ratio to see the effect of the plastic deformation in the soil specimens as well. And it has been observed that with an increase in the strain amplitude, a huge increase in the maximum pore pressure ratio as well as the residual pore pressure ratio occurred, especially after 0.5 Hertz strain amplitude. The dynamic properties of the soil, like shear modulus and damping ratio, were also studied in this, and it has, using the G value and damping ratio value, it has been observed that from 0.1% to 0.5%, a huge difference in shear modulus decrease was observed, indicating a very huge stiffness degradation in the soil after 0.5 Hertz strain amplitude in soft cohesive soils like in palette soil. And similarly, the damping ratio, although not much variation was observed in the damping ratio, still a figure has been attached to see the. Also, the stiffness degradation index was plotted. And these are the cyclic strength properties of the soft cohesive soil, where RUmax, G1, G200, D1, and degradation parameter were studied. So the main conclusions from this study, which we have obtained, that the inclination angle of the loops decreased with increasing cyclic strain amplitude, which signified the loss of stiffness in the soil. Then the peak cyclic stress mobilization increased with increasing strain amplitude. Also, the higher cyclic strain amplitude caused greater pore pressure evolution in the soil, in the soft cohesive soils. The shear modulus decreased, but the damping ratio was increased with the increasing strain amplitudes. The stiffness degradation in soft cohesive soil was also rapid, especially during the first 50 loading cycles. Then the cyclic degradation index also decreased with increasing amplitude, with a significant drop in delta for strain amplitude greater than 0.5%. Also, a 2.85-fold rise in the rate of stiffness degradation was observed when the strain amplitude increased from 0.1 to 1.5%, which highlighted the significant impact of strain amplitude on the stiffness loss of soft cohesive soil. These are some of the references. Thank you.
So thank you, Shweta. So any one or two questions we can take in case we have. Yes, sir.
Good presentation.
Thank you, sir.
You are using clay sand actually.
Yes, sir. Yes,
Then why you are calling a soft clay?
Sir, I am not calling it as a soft clay, but I am calling it as a soft cohesive soil because the
But it is
sand
not a
particles,
cohesive soil. It's a clay sand, predominantly sand only, no?
the sands are very finer part. In Palaj, the sands are very finer and mostly the clay dominates the sand. So the
Okay, I understand that. How
why
do you
I am
define
calling-
soft? You are saying soft clay.
Yeah.
What is the basis for that?
I am calling it soft on the basis of the UC strength which I obtained, which falls within the range of 25 to 50 kPa.
25 kPa, that's why you are calling.
Yes, that's why I'm telling the consistency to be.
Okay, thank you.
Thank you, sir.
Hello.
Hello.
Presentation was wonderful.
Thank you.
Can you be louder, please?
I just want to ask, you have obtained the dynamic properties of the soil, like shear modulus.
Yes, sir.
But you have not specified which shear modulus you have identified, like maximum shear modulus or tangent shear modulus. There are different types of shear modulus where we are calculating the dynamic properties of the soil. So which shear modulus you have calculated?
I have joined from peak to peak, like from 0 to the maximum stress which we obtain
Oh,
from
so
these 2 points. Yeah.
That is secant
Yeah.
shear modulus.
Not the tangent modulus.
Okay.
Yeah.
Okay, thank you.
Thank you, Shweta, for
Thank
your
you.
presentation.
Thank you all.
So for the next presentation, the topic is Analytical Framework for Estimating Excess Pore Pressure Redistribution in Liquefiable Layers. The authors are Sumit Kumar Sinha, Katrina, and Bruce Loy. So you'll have 6 minutes, Sumit.
A very good afternoon, everyone. It's a little bit involved presentation, but I'll try to wrap up in 6 minutes, which seems it is less, but let's try that. Okay, so in this presentation, I'll be talking about an analytical framework which has been developed to find out how does the excess pore pressure redistribution affects the liquefiable and non-liquefiable layers. To start with, let us consider a simplified profile where you have, let's say, a clay impermeable layer of clay, and let's say there is a liquefiable layer. I have written undrained. Assuming this layer can liquefy under undrained conditions, and then let's say below it there is a non-liquefiable layer. Again, undrained. In undrained conditions, assume it doesn't liquefy. Now, for here, when I say undrained, undrained means that if you treat that layer to be a separate layer, that is what it means to be an undrained condition. And what we want to do, what I will be talking about today is what happens if these layers are connected with each other, which is what the reality is. How does this excess pore pressure changes across these layers, and how does it changes the development of these excess pore pressures. So let us see what happens during an actual earthquake event. The data that I'm going to show you here is actually from a centrifuge test. So as the shaking begins, excess pore pressure starts to develop, as you can see. Of course, it will start to develop much higher in the liquefiable layer, and then it will slowly develop also in the non-liquefiable layer. At the peak of shaking, you would see some part of the liquefiable layer getting liquefied, and that's how your excess pore pressure becomes equals to the effective stress, whereas your non-liquefiable layer also develops some kind of excess pore pressure. Now, if we go with simplified procedures like Yod et al., Idris and Boulanger, what we would expect is, or Mele et al., what we would expect is the excess pore pressure shown by the blue line. So the question is, why does that not happen? All these empirical procedures, they would say the entire 8 meters of the liquefiable layer would liquefy, but in reality, it does not liquefy. So why is that? And the answer to that is basically the redistribution that occurs between these layers. Because these two layers are connected with each other, so water can migrate from one layer to the another. So let us try to understand what really happens. So again, let us assume that these layers are independent, which means they don't interact with each other. So the simplified approach would give you this result in terms of excess pore pressures. So the liquefiable layer would liquefy, and assuming the non-liquefied layer would generate no excess pore pressures. But imagine, since these layers are connected, as soon as this happens, there is a large gradient of excess pore pressures across these layers. So as soon as this happens, actually water will seep through from the liquefiable layer to this non-liquefiable layer. And that will happen, and slowly more water will go, and that's how the excess pore pressures will start to change between these liquefiable and non-liquefiable layers. And after some time, there will be equalization of pore pressures that will achieve, which is shown by T4, and then slowly T5, T6, and eventually, if you leave it for a very long time, all these excess pore pressures will dissipate. So what we saw in the centrifuge test is shown by this yellow line. So we saw this yellow line, not that blue line. So the question is, what is going on? How can we explain this thing? And how can we model? How we can correct our simplified procedures? In this paper, we have developed a simplified procedure. And we have shown here that this simplified procedure can explain this excess pore pressure difference that we observe in the centrifuge test, and what we predict using simplified procedures. So, okay, I'll skip because I don't have much time. You can see here on the figure on the bottom right, what we see from the centrifuge test is shown in red. What simplified procedures give is shown in blue, and what the procedure that we have developed, analytical framework, is shown in green. So let me, already 5 minutes, 30 seconds. So let me explain how this approach works. To start with, we have considered two-layer system. So first, you can see that on the right side, in the first one, we assume, let's say there is a NLU layer, non-liquefiable layer, above a liquefiable layer. And the second one, we have considered a base case where there is a liquefiable layer above a non-liquefiable layer. And what we have to do is that if we want to find out how does the redistribution affects the excess pore pressure generation, what we can do is we can write down the volume conservation. Assuming the blue line is the excess pore pressure in the undrained condition without considering the interaction, and the red one is because of redistribution, we can write down the equation as shown here below, and our objective is to find out what is the redistributed excess pore pressure that will be caused by that. So we can solve it. results in these kinds of equations. We don't need to look into that. But what we can see here from the chart is on the x-axis is the compressibility ratio and the thickness ratio of these individual layers which are interacting, and the y-axis is the redistributed excess pore pressure. That is the excess pore pressure that will develop after redistribution. And you can see if I have a liquefiable layer, which means excess pore pressure is 1 initially, and I have a non-liquefiable layer, I can't use pointer as well. Pointer is not working. So it's very difficult to explain. But if you look at this graph, if you have a non-liquefiable layer where excess pore pressures because of the earthquake is 0, because of the interaction, you can actually liquefy this non-liquefiable layer. And you can also prevent liquefaction in the liquefiable layer. And you can see if your H and MV bar is very small, then your excess pore pressure, both in liquefiable and non-liquefiable layer, will essentially become 1. But if your H and MV, relative compressibility and thickness, is very large, then it can prevent liquefaction in the liquefiable and non-liquefiable layer. I'll just skip that. Sorry for going very fast, actually. I would recommend you read the paper if you are interested in.
Please wind up, Sumit.
Huh?
Please wind up.
Yes. So in the first part, we looked into how does the redistribution occur. We never talked about the time, but in reality, during an earthquake, this redistribution happens during the earthquake itself, which means the condition during earthquake is not undrained, it's partially drained. So we also derived an equation, okay, what happens during the earthquake if the redistribution occurs. This chart basically helps you in finding out what is the minimum thickness of the liquefiable layer we can have that can be actually prevented from liquefaction because of this redistribution. Just to give you a small calculation, then I'll wind up. If we assume this time ratio of 1, we can find out that this minimum H and MV bar will be 0.3. And if you assume that MV bar ratio, which is compressibility of non-liquefiable layer with liquefiable layer, is 1 over 1 by 20, and thickness of non-liquefiable layer is 1 meter, we can say that 167 millimeter, which is 16.6% of the liquefiable layer that we have assumed that is going to liquefy actually does not liquefy. So that helps us because if we can understand that a liquefiable layer doesn't liquefy, we can save a lot of money, and because we don't need to treat that. So I'll just come to conclusion quickly. So here we have developed an analytical framework to evaluate redistribution in soil layers. The framework has been validated against centrifuge tests or hypergravity tests. What we have seen is redistribution increases excess pore pressure in non-liquefied layers, which can reduce the tip capacity and cause settlement in the piles if the pile is embedded in non-liquefiable layers. And redistribution decreases excess pore pressures in the liquefiable layers, which can enhance liquefaction resistance and potentially prevent layers from liquefying. We have also developed a framework and charts to determine what is the minimum thickness of the liquefiable layer that can prevent from liquefaction because of this redistribution. And finally, we have also developed an Excel spreadsheet, which I just skipped very fast, which can be directly used to find out what is this redistributed excess pore pressure and how this can be used. So thank you so much, and thank you for giving me the extra time.
Thank you, Sumit. Any questions in this presentation, you can directly contact Sumit, maybe outside the conference hall. Thank you. So we go to the next presentation. Undrained cyclic response of Indus Basin sand in Leh, Ladakh. The authors are Abid Ahmed Sofi and Majid Hussain. Yeah. Please stick to the time of 6 minutes, please. It's there. 9 is there, but you take 9 is.
Abid Ahmed Sofi, PhD student student from NIT Srinagar, along with me, my supervisor, Dr. Majid Hussain. I am going to present my conference paper with the title Undrained Cyclic Response of Indus Basin Sand in Leh Ladakh. This will be the outline of the today's presentation. Firstly, I will be highlighting the study area for the study and problem statement. Then after, objectives, concept of liquefaction, methodology adopted for the study, and some key findings. This is actually a sort of case study. The study area for this study chosen is Leh Ladakh. Leh, as we can see from the map, it falls in the northmost part of the country. As per seismic zonation, this Leh Ladakh, it falls in seismic zone 4, where we have high seismic vulnerability. We have high seismic vulnerability and high susceptibility to strong ground motions. As the study area falls in zone 4, we have very less data available for designing of structures, since this area of Leh, the construction is booming in this union territory, but we have very less seismic data available for designing. In the Leh town, we have a site where we found granular deposits in the form of fine sand, and the water table was encountered at very shallow depth. These two factors make the site favorable for liquefaction risk. In liquefaction, if it happens, the effective shear strength is lost. The result will be large deformations, settlements, and the underlying soil is no longer able to support the structures. This will be the objective of the study, to investigate the cyclic response of Indus Basin sand, assess liquefaction susceptibility under earthquake loading. Actually, we are going to measure the liquefaction resistance in terms of CRR, cyclic resistance ratio. These are the factors that affect the liquefaction, which includes soil type, degree of saturation, void ratio, cyclic stress ratio, confining pressure, frequency, and fine content. These were some basic properties of the sample that was used for the study. Having specific gravity of 2.67, the sample is 50 by 100 were used to do cyclic triaxial testing. The samples were compacted at relative density of 50%, followed by carbon dioxide flushing, then saturation by backwater saturation, and then consolidated at 100 kPa. Cyclic loading was varied at different CSRs. To define the liquefaction, we used a double amplitude of 5% strain. Whenever the strain reaches to 5%, more than 5%, we can say that the initiation or the liquefaction process has initiated. This was a setup in our lab used for this study. We have this cyclic triaxial setup. In the bottom figure, we have the sample. On the right-hand side, we have the failed sample of liquefaction. This is the gradation criteria for selecting the sample to be liquefaction prone. These two red lines, these make the high risk band of the sample, our sample falls within the region of this red band, having high liquefaction risk. These were some of the results where we do testing of the samples at CSRs, CSR 0.1, 2, and 3. In CSR 0.1, the axial strain, very low axial strain was observed, and the pore water pressure up to 10 to 15 cycles, the pore water pressure raised and then remained constant, and the test was continued until till 100 cycles. No liquefaction was observed at CSR 0.1. As the CSR was increased from 0.1 to 0.2, liquefaction of the same sample at same relative density was observed almost at 24th loading cycle. And when the CSR was increased to 0.3, liquefaction was observed at the initiation of the liquefaction was observed at 12th loading cycle. This is the hysteresis pattern of the three samples. At 0.1 CSR, we have quite low axial strain developed. On the left-hand side, at CSR 0.2 and 0.3.
Abid, your time is up. You can wind up.
1 or 2 minutes. For CSR 0.2 and 0.3, at lower strain, lower strain was observed for initial cycles, and then we have the process of liquefaction was triggered at higher axial strain. This is the effective stress path for 3 CSR 0.1, 2, and 3. As it is observed, the mean stress, it decreases with the loading cycles. This is the behavior at low, medium, and high CSR. At CSR 0.1, the sample was found more resilient and stable response was observed with minimal pore water pressure build-up. At CSR 0.2, progressive strain accumulation was observed. At CSR 0.3, rapid instability and rapid pore water pressure build-up. Cyclic liquefaction was observed in 12 cycles. These are the key findings. We can say that at CRR 0.7, 15 loading cycles for CSR 0.1, 0.27 can be calculated by the interpolation from 3 CSRs. We can say that the sands at the site, they are highly vulnerable to seismic action. Before going to design or construction, we should investigate the site for liquefaction. These are some of the reference. Thank you.
Yeah. Thank you, Abid. Any one question? If we have time for one question. Okay, thank you. So then next presentation topic, seismic response of Imja Lake Moraine Dam and outlet structure under Kobe and Chile earthquakes. See, authors are Dangi Chetri, Tiwari, Sapkota, and R.C. Tiwari.
Good afternoon, everyone. I am Achal Tiwari from IOE Pulcher campus, Tribhuvan University, Kathmandu, Nepal. The title of my presentation is Seismic Response and Instability Analysis of Moraine Dam of Imja Glacier Lake. This is the structure of my presentation. Moving towards the background, glacial lake forms behind the natural dam of ice, rock, and debris. They appear where glaciers have melted or retreated. Leftover sediments and ice block the water flow. Meltwater and rainwater accumulate to create the lake. So these are the typical glacial lake types. So my study area is Imja Glacial Lake, located in Solukhumbu district, Nepal. It covers the Khumbu region, basically. So these are the streamline patterns of the Imja Lake. So Imja Lake has lateral moraines on the north and south sides, and lake is surrounded by lateral and terminal moraine. This is the lateral moraine, this is the terminal, and this is the Imja Glacier. So this is the seismicity plot of the study area. As we know, the Nepal face high risks of glacial lake outburst flood. So these are some of the GLOF events recorded in Nepal based on the different literature types. Why it is needed for study is, as we know, Imja Lake is one of the most studied lake. From 1985 to 2015, the area of Imja Glacial Lake has been doubled. This is the picture before the construction of the gate. And after the construction of the gate, from 2015 to 2021, the area increased by 20%. That means before and after the construction of gate, the expansion rate is found to be somehow similar. So the main objective of my research is to study the static and dynamic stability condition of terminal moraine dam of Imja Glacial Lake at different sections, to study the effectiveness of lake lowering, to evaluate the seepage characteristics of the dam to understand the potential seepage pathways, to compare the stability condition of terminal moraine in dynamic condition at different magnitude of PGA. The limitations are the terminal moraine of the glacier lake is not uniform in cross-section throughout the length. But for the simplicity, the analysis is done in 2D plane strain condition. The ERT conducted along the terminal moraine is extrapolated throughout the model, and the temporal variation of properties of moraine mass is not included in the study. So this is my methodology. I took my geometric data from topographic and bathymetric survey, and moraine dam internal structure is studied. Subsurface structure identification of terminal moraine is done, and then complete model is taken for the analysis. Moraine properties is determined, and I performed the finite element analysis by using Plaxis 2D software. I did static and dynamic analysis and took the output and performed the analysis and finally draw the conclusion. So this is a topographic map of the area which was taken from UNDP 2014 ERT investigation for structural design of Imja Lake lowering. This is the bathymetry map of area taken from ADAPT Nepal 2014. So the complete map from the topographic map and bathymetric map is digitized by using the AutoCAD software. So the different researchers have done the ERT at different section of terminal moraine of Imja Glacier Lake. The ERT test was done by Takinaka et al. 2010, which is used as a reference. This is the ERT line. This is the analyze section. And according to the Takinaka et al., he determined the inverse resistivity profile along the survey line EE dash, that is 630 meter long from a 2D 3D resistivity survey. Zone 1 indicates dead ice, Zone 2 consists of poorly packed debris containing large ice blocks, and Zone 3 represents high moisture debris with fine-grained material filling the gaps. Similarly, in case of CC dash, it is 150 meter long, and Zone 1 indicates dead ice. Zone 3 represents high moisture debris with fine-grained material, and these are some of the material with its respective resistivity value. So this is our profile which we made by using Plaxis 2D, final cross-section for the analysis. These are some of the collection of input parameters for stability analysis, which is seepage and deformation based on different literatures. So we perform the static analysis in 3 phases, gravity loading, deformation, and phi C reduction. This is the seepage analysis. The pore pressure is generated in initial phase using steady-state groundwater flow. 2-side boundary and top surface is considered. 2-side boundary is open boundary, while the bottom is closed for the flow analysis. In case of unsaturated zone, we use Van Genschutten hydraulic model in our software. For static stability analysis deformation, we use a 15-noded triangular element, which is used to represent the moraine dam. And 2 sides of the model boundary condition are applied by normally fixing the vertical boundary and making the lateral displacement to 0, whereas the bottom boundary is fully fixed while the top surface is found to be free. For the dynamic analysis, I used modulus of elasticity, Poisson's ratio, and density, these parameters, to determine the shear modulus of soil and the shear and compression wave velocity. These are some of the material parameters used for dynamic analysis based on the literature. For the dynamic analysis, the 2 vertical boundaries are applied by free field boundary condition, whereas the bottom boundary are applied by compliant base boundary condition, which allows the incoming wave to pass from the boundary but absorb the outgoing waves. So here we use alpha and beta. They are the Rayleigh coefficients, and they used to determine the target damping ratio. And the damping matrix is defined by C equals to alpha m plus beta k, and it is used to determine the equation of the damping matrix. So this is the input of target damping ratio and frequency in the Plaxis 2D. This is the time history plot of Gorkha earthquake 2015. This is the geometrical model of moraine dam for the dynamic analysis. So phases during analysis are dynamic analysis, plastic nil phase, and phi C reduction. So moving towards the result and discussion, in case of static stability analysis deformation, the maximum displacement seems to occur at the downstream slope of the moraine of magnitude 1.95 mm. In figure 24, the steady state CPS flow through the moraine is estimated as 4.937 epsilon minus 6 meter cube per second per meter length of the moraine, whereas figure 25 represents the presence of dead ice at the upstream slope, which acts as a cutoff for the CPS flow through the moraine. So the total factor of safety of terminal moraine in static condition is 3.182. That means as per United States Bureau of Reclamation, we found 1.5. So our static analysis is safe enough according to our value. So this is the peak excretion amplitude at different location of the moraine dam in case of dynamic analysis. This is the symmetric half plot. Here we can see the peak excretion at different location. At 5 meter from the bed, the excretion value is found to be high. But as we reach to 250, excretion increases and then slightly decreases. At the peak, excretion increases to 0.344 meter per second square. So this is the total displacement at the end and post-earthquake motion. We found
please wind up, Mancha.
Okay. Maximum displacement is 46.71 at the end, whereas post-earthquake is 14.76. These are also the maximum horizontal displacement 12, and vertical is 8.8 centimeter is found. So these are some of the total displacement factor of safety. Here we can see the factor of safety of terminal moraine is decreased from 3.18 to 3.03. That means factor of safety alone may not be the governing criteria. Parameters such as displacement, stress, and strain could provide a reliable measure of stability. So location of outlet structure done by Takinaka et al. Is 2010. It is used as a reference to determine the internal structure of terminal moraine. These are the RT line and analyze section. This is a topographic map below the downstream added by Google Earth. Location of outlet structure. The static condition deformation is 7.386. And post-earthquake displacement, horizontal 9 centimeter and vertical 8.8 centimeter is found at gate section. So here we can see the dynamic condition, the factor of safety 2.97. That means gate section is critical compared to dam section. So this is the peak excretion amplitude at different location of moraine dam. This is the symmetric half plot. This is the response spectrum. The maximum value is at 1.6 second. So I validate my result, and the total CPS discharge obtained from numeric analysis static condition is 4.937 epsilon minus 6 meter cube per second per meter length of moraine. And considering a 700 meter wide moraine, the total CPS discharge is 0.0035 meter cube per second. And this is my conclusion. That means two-dimensional finite element analysis shows the Imsa glacial lake terminal moraine is stable under both static and dynamic condition. Factor of safety 3.182 and 3.0 for static condition, reduced to 3.03 and 2.97 for post-earthquake. CPS discharge is low. Dead ice acts as a CPS cutoff. Okay. Stability is high under current condition, but may decrease under strong PZ events, that is Kobe and Chile earthquakes. Now I would like to move towards my next presentation of Kobe and Chile.
No, we'll take that afterwards.
Sorry?
We'll take it later. Let other presenters have their presentation.
Okay, I will present my next presentation at the end, okay?
Later, after the rest of the presentation.
Okay, thank you so much.
Thank you.
Thank you so much.
Yeah. So any questions, you can, audience requested to talk to her directly. No, you have taken time, ma'am. Thank you. So we'd like to call upon the next presentation topic and the speakers. So it is, effect of seepage and suction on liquefaction resistance for unsaturated soil. So Nishimura and Masafumi Matsumoto.
Thank you, Mr. Chairman. And this is by considering the unsaturated soil and the dynamic properties. This is the background, and the excavate widely reported it as infrastructure. And I think that the unsaturated soil embankment, the concern in the rising severity accident include the unsaturated soil structure. Previous working and particularly report to the stress control under the cyclic stress test and some gravel mixing and the considering the gravel content and relative density in the unsaturated condition. Okamura considering the assessment of the liquefaction resistance and the clean sand, however, that he not touch the control the asymmetric section are limited to the and degree of saturation in explaining the unsaturated soil liquefaction. Me and try to the development using the membrane instead of the high air into disk. As you know that the unsaturated soil suction controls in generally and use the ceramic disk. This is purpose conducted the major cyclic stress test for unsaturated soil and with the saturated soil and unsaturated, saturated, unsaturated, saturated, unsaturated condition. And the variations cyclic stress relation applied to the specimen and the measures for water pressure through the cyclic loading test. Finally, I show you that the cyclic stress ratio and the number of cyclic number, as you know that the liquefaction resistance. And I use the soil material, non-plastic 30 soil, all of the soil specimen and statically compacted. Size is 100 and the diameter 50 and a water content 70% limited. And then change it to the dry density 1.47 and 1.3 and magnitude mg per square 3. This is the apparatus for standard and liquefaction test in the two-lecture style. A testing program of first resection control performance, saturated specimen, conducted out under the pressure membrane technique. All specimens will measure the negative water pressure for unsaturated specimen for the guarantee taking the measurement quality for negative water pressure. And the next one, 1.4, two kind of the dry density, and above the relative confining pressure, 20 and 50 in relatively small confining condition because the large confining pressure induced by the large shrinkage. Result going to the result, and is the water content and the section relationship by using the microporous membranes. Water content increasing the section, decreasing, and the limited the range is so possible to express the straight line is verifying the data set. Next one, going to the cyclic behavior, axial strain, and the unsaturated soil number of the cyclic, and this test result show look at the deformation occurrence is expansive expansion side. Okay, dry density 1.487. Next one, cyclic stress relation up to the 50, the almost the constant cyclic stress ratio. Next one, export pressure through the microporous membrane. As you know that the so small changing the so negative pore pressure, however, a little bit the so increment the so excess pore water pressure is that the matrix section decreasing in meaning. Next one is also the saturated condition, and like this is expansion side, so large and deformations. This is a saturated condition, and compression side and the expansion side is also very big. It is a large deformation is that the reduction of the liquefaction resistance. As you know that so as and comparing the saturation condition, that is so lost of the liquefaction resistance like this. Okay, so say this is the resistance. Time is up. Okay, and the cyclic stress ratio and number of the cyclic, and all of the unsaturated soil, and increasing the dry density is increment the stress ratio. However, that the soil and the saturation is going to the zero. Very clearly is the effect of the saturation. Summary this even conclusion. Thank you very much.
Thank you very much, sir, for your presentation. Any questions? One question can be taken. Okay. So no questions. Thank you, sir. Thank you very much. So moving to the next presentation, the topic is comparative study of liquefaction potential of core areas of Kathmandu Valley using microtremor measurement. Authors are Sanjeev, Khemraj Pokhrel, and R.C. Tiwari. Please have a note on the time clock that is there in front of you. Thank you.
Good afternoon, everyone. Today, I am going to present on my research topic, comparative study of core area of Kathmandu Valley on basis of liquefaction potential, where there is comparison between microtremor analysis and numerical investigation is done. My team, I have Sanjeev, my supervisor Ramchandra Tiwari sir, and I am representing also a Nepal Geotechnical Society, working as a executive member too. My presentation goes like this. So Nepal is made with the earthquake. So we have the Indian and Tibetan tectonic plates. So the Nepal is suffering from the various major earthquakes from past history. So starting from 1934 to recent Gorkha earthquake, 2015, due to the amplification phenomena, and there's a composition of lacustrine deposit in the Kathmandu Valley. Since in past there was a lake where there is a various sediment deposition are found undergoing the geophysical investigation. So due to that reason, when any seismic activities occurs, so at that period, due to compacted sandy soil, our Kathmandu Valley has a high chance of having liquefaction, where the sand get boils, the lateral spreading occurs, and sometimes the settlement also occurs. If the foundation design are very wrong, then in that situation, the settlement is also occurring in previous seismic activities. So due to that reason, the main reason of my research is to protect and to get aware about the liquefaction, as well as to prevent ourselves from the various amplification phenomena too. So my site selection is the Kathmandu Valley, which is the geomorphological formation is like this, where there is a lacustrine deposit, and it is also validated from the past literature too. And from the various last study from UNDP to various other researchers, liquefaction susceptibility map and hazard map has been developed, and the various potential region has been identified.
So this is my country, Nepal, and where I have selected the Kathmandu Valley for the liquefaction potential study. So in Kathmandu Valley, there are 3 districts, Kathmandu, Bhaktapur, and Lalitpur, which is the smallest district. And there is a Kalimati formation, there is a lacustrine Kalimati foundation is found in the Kathmandu Valley. So I want to, next slide. So my basically major principle is in terms of microtremor analysis, I have used the HBSR, horizontal to vertical spectral ratio, which was given by scientist DeLange et al. In 2000, where the 3 component measurement are done in 3 directions, north, south, east, west, and up and down. And another to validate it by numerical investigation, I have used pore water pressure ratio, which is done by the Plaxis modeling, where the 2 stress initial and total stress is ratio is calculated. So moving forward, so this is the Plaxis pore water pressure ratio formula, and the finite element modeling is done in the soil up to 30-meter depth only. And moving forward, so the microtremor, the instrument uses the microtremor with sensor, geophone is there. So this instrument is kept in the surface of the soil, and about 30 to 45 minutes, the continuous measurement is done in the very sound environment. So especially the measurement is done at the night time, so that external noise and disturbance will be neglected. So, and the completely SISAME guideline is used to analyze the SBSR analysis curve. So, and similarly, moving forward, in Plaxis modeling, numerical modeling, UBC modeling, University of British Columbia is used for the case of sandy soil, whereas in case of clay and silt soil, generalized soil modeling is used. So, various dynamic soil parameters are also taken out from this model parameter. So it goes like this, and where SPT value, N value is also taken from various borehole data. So I have taken 29 boreholes in the Kathmandu Valley, which lies along the 3 districts, Kathmandu, Bhaktapur, and Lalitpur, to validate those new microtremor analysis data, nearby borehole data are taken. So moving forward, so these are the new microtremor analysis SBSR curve. So I have only shown the some sampler analysis. So where the amplitude versus frequency is plotted, which is obtained by converting the time domain analysis into frequency domain analysis using fast Fourier transform. So these are the graph. So from this graph, we finally calculate the liquefaction potential susceptibility index is calculated, which is denoted by Kg, which is the ratio of amplitude by frequency. So these are the 2 sites, Mardol site and Atiban site, which lies in the Kathmandu Valley. So can I move to next slide? So in the Plaxis analysis, the soil modeling is done, and we finally obtain the pore water pressure ratio is obtained. So those regions where the value of pore water ratio is 0.7, so this indicated by the red zone are indicated in those regions, and which are in the other indication below 0.7, they are less susceptible to the liquefaction. And finally, from this 75 microtremor analysis, we found the susceptibility index is calculated, which is donated by Kg. And finally, in nearby station, can I move to next slide? And also, from the numerical modeling, the value of pore water pressure ratio is calculated, and finally they are plotted and interpolated in JS map. So finally we obtained that in those regions where in the site investigation by microtremor analysis, where the value of Kg was more than 5, we found the liquefaction potential RU value was found to be more than 0.7. So these are the reasons where the liquefaction was accepted, and in the 3 districts it was individually calculated, and finally Bhaktapur, Lalitpur, and next one is Kathmandu. So this is the Kathmandu region. And in order to validate this map,
Sanjeev, can you conclude, please?
okay, can we move to next slide? So this is the validation of the various region, especially in Hattiban and Imardol region. We found the value of Kg to be greater than 5, so which was also practically same during the Gorkha earthquake too. So we were suffering from the liquefaction during that seismic activities. And I want to show some picture of the liquefaction that was found in the Gorkha earthquake. So finally, I would like to conclude that in Nepal, especially at the capital city, Kathmandu, there is a high chance of liquefaction. So we should be aware, and practical investigation, geophysically as well as numerical modeling should be done, so that in further earthquake activities, we will be safe from the liquefaction. And furthermore, I want to recommend that we only applied the small instrument, which was not that much sophisticated. So by undergoing to MASW analysis, more precise result will be obtained, so that in my further study, I will include that MAM survey will be included, area survey. Thank you for listening to me. Thank you.
Thank you, Sanjeev. Thank you. Any question? One can be taken. Thank you. Thank you very much. So I would like to go to the next presentation. Effect of nonlinear soil behavior on seismic performance of a zoned embankment dam, A. Kumar and B.K. Maheshwari.
Good afternoon, everyone.
Alok,
I am Alok Kumar.
stick to the time, please. So there is a timer in front of you.
Today, I'm going to present my topic, effect of nonlinear soil behavior on seismic performance of zone embankment dams. These are the outline of my presentation. Coming to the introduction, as we all know, dams are the lifeline of civilization, and as a definition, we can call it as the barrier across a river, stream, or waterway to control and confine water flow. Its purpose varies from irrigation, hydroelectric power generation, flood control, domestic and industrial water supply. They can be vary from small earth embankment dams to massive concrete structures. These are the worldwide data of the dam. Most number of the dams are present in China, followed by USA and India, and out of these, earth and rockfall dams contribute to the almost 80% of the total dams. These are the objectives of my presentation. First one is evaluate the stability of Chang Dam under static, pseudostatic, and dynamic loading condition. Then I perform numerical modeling using GeoStudio and investigate the influence of nonlinear soil behavior on stresses during seismic loading. And last, compare linear and nonlinear soil model for seismic performance evaluation. For this purpose, I have chosen the Chang Dam, which is located in Kutch, Gujarat, having seismic zone 4 and Z.24. It was constructed in 1959, and these are the dimensions of the dam. These are the material property taken from the literature. Finite element modeling has been done, and 2D mesh is generated having average element size of 1 meter. Boundary conditions are as given. Seepage and initial stress condition were evaluated. Steady state seepage simulation were conducted for the reservoir level of 14 meter, and these are the phreatic line and pore water distribution for evaluated from CFW analysis. And in situ stress generated with sigma W. Slope stability analysis were conducted for static and pseudo-static analysis, and dynamic analysis has been done for the dam using a Bhuj earthquake time history. Coming to the result and discussion, factor of safety for upstream condition in static condition was found to be 2.05. For downstream slope, it was 1.56. For pseudo-static condition, factor of safety reduced to 1.49 for upstream slope and 1.21 for downstream slope. These are the counters of horizontal stresses. From this, we can see that for linear elastic model, maximum horizontal stress was found to be 273, and for nonlinear model, it was found to be 291.12. And there was a percentage increase from nonlinear to linear by 6.6%. Same is for vertical stress. In this case also, the stresses were increases by 15.6%. Coming to the conclusion, the dams remain stable under static conditions and with adequate factor of safety for both upstream and downstream slopes. Seismic loading significantly reduces stability, especially on the downstream slope. Nonlinear soil behavior result in higher stresses compared to the linear models. Vertical and horizontal stresses increase by 15.6% and 6.6% respectively under nonlinear analysis. These are the key references. Thank you.
Thank you. So thank you for finishing it before time. So any questions on this?
Yeah, hi Alok, I have one question. How you decided the soil property of the zone dam? Any investigation has been carried out or?
It was taken from literature.
Okay,
Yes,
and I saw that the PGA which you have used is peak ground acceleration values, which is somewhere around 1.1 G.
0.11 G.
But
0.11 G.
yeah, but the PGA into that region where this dam is available is around 0.24 G or 0.2 G.
0.24.
It's in the zone 4 of seismic region, right? So the expected PGA is around 0.24 or even higher. So why you have used this 0.12
Seismic
G?
coefficient is generally taken 1/3 to 2/3 of the Z value.
Sorry, say it again.
The seismic coefficient, that is horizontal seismic coefficient, generally we take 1/3 to 2/3 of that value.
Is there any basis for 1/3 or 2/3? That particular is not there in your presentation. Why I should consider 1/3 or 2/3? Is there any logic?
I will see.
Okay. Okay, thank you.
Thank you. Thank you, Alok. So the topic of the next presentation is monitoring ground vibration during blast-induced demolition of coal tower and chimneys. Authors are Alina, Tarun, Bhuminathan sir, Anil Joseph sir, and Dhanya.
Good afternoon, everybody. Welcome to my presentation. My presentation is on monitoring ground vibration during blast-induced demolition of chimneys. So this is the brief content. Introduction, pre-implosion assessment and protection, vibration measurement during implosion, post-vibration assessment, followed by conclusions. So blasting-induced collapse are predominantly practiced worldwide, mainly in the mining industry in the past. Later on, it gradually shifted towards building collapse. But maybe up to the past 20 years, it was mainly focused on collapsing industrial structures in rural locations. such a way that there is clearance between one structure to the other. So the blasting activity is not hindering the other structures or equipments or anything nearby. But in the recent past, the multi-storied buildings are in rise, and in several situations it became mandatory that you have to collapse buildings in very densely populated urban areas. So in India, maybe it was in 2019 that we had a major demolition-induced building collapse in Kochi, where they had to bring down 14 to 18-storied flats through the process of implosion, mainly due to violations in construction. They didn't get proper approval from the government. So such kind of things keep happening. And since then, it started a new wave of demolition processes for high-rise buildings. It gave confidence for the country that we can take up such projects in the urban area without causing disturbance to nearby structures or collapse of the nearby structures. So practically, building demolition through the process of implosion means that we are using explosive to induce a massive structural collapse inward, in opposite to the explosion process where we are exploding or taking the materials in the outward direction. Here we are bringing the material inward such that the whole building is collapsing within its own footprint. And usually this happens within seconds. The main advantage is that it's very safe, quick, and environmental friendly, because the pollution that is with the mechanical collapse for a period of years can be brought down. So these are mainly for high-rise buildings in dense city centers and in constrained environment. So looking at the mechanism of the collapse, if we break it down, firstly, the structure, that is the main point of concern. The structural analysis part has to be carefully taken into consideration to see the load transfer mechanism, or how the load path is being distributed along the structural members in the beam column setup. So once that is decided, you know how the loads are being transferred. You can remove or pre-weaken the non-load bearing members, such as the brick walls or any beam or staircases that is not going to help in the load transfer. With that, what happens is that the dead weight of the building comes up, and finally you are left with maybe 50% of the weight of the building that needs to be come down. So once this is established, so we need to decide on the placement of charges on columns or beams. In a way, you have to place the explosives at critical locations so that the building is coming down in progressive collapse way. Instead of one single collapse, it is coming down through blasting-induced collapse as well as with its own weight or free fall. So this is to be carefully planned. And progressive collapse inwards, these blasters, they decide, they will explode the major support columns on the lower floors, followed by few upper stories. So that is the final stage. So ground-bound vibrations, due to other construction activities, the research in that area is ongoing for a very long time. But because these are case studies, the research on this area is very limited, and we have to rely on mainly actual practices in the field. So blasting-induced ground vibrations mainly has two components. One is that there is an actual blasting that is going on, that is going to create shock waves. And second is that the building is hitting the ground, that is again going to convert into seismic waves, that is the surface waves and the body waves. The surface waves to the surface, and the waves that is being transferred get converted to body wave and then get reflected back to the surface. So there is another phenomena that is very much beneficial for us, that is the damping mechanism. So once the vibration is hitting the ground, unlike the other seismic waves, this is going to attenuate at a very higher rate. Also, it depends upon the soil properties or geological conditions at the site. That makes it challenging also, because you cannot decide how the waves are going to attenuate comparing one site to the another. It depends, the waves amplification and de-amplification depends upon the soil conditions as well. So blast-induced ground-bound vibrations, usually ground-bound vibrations are measured in peak particle velocities, because we have standards, and it's highly correlated with the limits of potential damage to structures. So one good quality of the blast-induced vibration is these are very short duration vibration compared to other seismic activities. So the vibration is going to stand for a very small time. And second, based upon the fewer case studies that has been published, the vibration has found to be falling at higher frequency ranges. That is a good thing because it's standing away from the natural frequency of tall buildings. However, the major concern is that peak particle velocity. The amplitudes might be very high, and this can create problem to nearby structures, especially that is in the close vicinity, maybe 200 meters to up to maybe 500 meters from the area of blasting. So these can cause immediate damage regardless of frequency, including the adjacent structures the structural members can crack, structural elements can get weakened, and another challenge is the debris flow. If things goes in an explosive way, the debris can fly to several hundreds of meters, and one debris flow can cause problems to humans and other structures.
Dhanya, your time is up.
Yes, sure. So the project is that Jamshedpur the steel plant. It is located in Jamshedpur, and the main thing that is going to collapse is 2 RC chimneys, 110 meters. The soil is lateritic deposits overlying weathered rock. So this is the location of the coal tower, and nearby structures are 3 main concerns are towers, gas pipelines, and 2-story building at risk from vibrations or debris. So prior to demolition, vibration, visual inspection, and NDT on all these surrounding structures were carried out, or the rebound hammer test kind of things to assess the strength of the concrete of the nearby structures. Second is that this is a collapse trajectory, and you can see the chimneys. So this is predetermined, such a way that it's falling without disturbing the surrounding structures. So in that trajectory, protective measures such as impact cushion berms are constructed, and perimeter curtains, water sprinkling for dust or debris control is being carried out. So this is the implosion and vibration measurement setup. It is primarily the hinging mechanism that we use to collapse trees. You induce the hinge at one side, and the building is going to collapse in the exact opposite direction. So vibration measurements are carried out at 10 locations, approximately 100 meters within the radius of the collapse. And geophones and accelerometers were used as measuring devices. So this is the result. Combined blast and fall induced vibration time history. You can clearly see that there are 2 distinct vibration amplitudes. One is pertaining to the blast activity, that is in a very short duration, and followed by fall or the touchdown vibrations. This is a frequency spectra, and this is the values for the vibration during demolition. And the values are within the limits are within the safe levels as proposed by DIN, or the German standards for vibration control. And the frequencies are also at higher levels. So overall, this is a post-blast survey in that it is found that minor widening of pre-existing superficial cracks or no structural damages were reported, and the whole system is found to be in a safer way. So the main conclusions are that in this demolition process, vibration levels remained within safe and regulated limits. The vibration mitigation measures, that is active vibration control near the source of the vibration, is another crucial thing that could have benefited this attenuation also. And the subsoil conditions might have given a logarithmic decrement in the attenuation of the waves. And real-time monitoring is always good because it gives an upper hand to the client as well as the owners of the adjacent buildings to reclaim the money if anything goes wrong. So it is finally, the recommendation is that with available case studies, it is proposed to build real-time empirical relations and numerical simulations so that a predictable model is being developed. Thank you for your attention.
Thank you, Dhanya. One question, anyone? Okay.
Is there any impact on the soil profile or soil properties on this attenuation and the vibration pickup?
Yes, sir, definitely.
Yeah.
When the type of soil changes, it depends upon the material damping as well as.
Okay, so in this case, have you studied the soil profile impact or soil profile of it?
No, sir. This has been numerically studied by changing the soil properties.
Okay, thank you.
Dhanya, in your first slide, you had mentioned that it is maintained within the footprints of the building. So any demarcation or any boundary that we set, or it depends on the profile of this building?
It depends upon the profile of the building. Usually it is like within maybe 1.2 times the radius of the building.
Okay. Thank you. Thank you, Dhanya. Round of applause, please. Okay. So we go to the next presentation. Small strain dynamic behavior of a coal mine overburden waste. The authors are Kaushik Das, Debjit Baumik, Bappaditya Manna, and Ramanathan Ayodhiraman. So the timer is there right in front of you.
Good afternoon, one and all present here. So the topic is small strain dynamic behavior of coal mine overburden. So this work is a collaborative work between IIT Delhi and NIT Silchar. Second author, Debjit Baumik. I am from NIT Silchar. So I thank Kaushik to do the work and give me the opportunity to present. So coal is the most important and abundant fossil fuel in India. Still, it is the most popular fossil fuel that we use. And there are mainly two methods, open cast mining and underground mining. Among these, open cast mining is the most popular one. 90 to 95% of the coal is collected through this method. The coal mine overburden, that is in short OB, is basically produced during the blasting of open cast mining. It is composed of soil, rocks, and other geotechnical material that is present over the coal and must be removed to access the coal. So increasing problem with large amount of OB dumps is a major problem. Main problem is the land reclamation after the mining, and it is not that popular to use as other means as a geotechnical material, so which is having a possibility of using it for different purposes. So the production of overburden removal are increasing day by day. You can see that in 2022-23, the total mega cubic meter of 2,469 was created that year. So the potential use of OB, geotechnical engineering, are as backfill application in geotechnical engineering. It has a great potential to use as a construction material and geomaterial. The different major applications are backfill material, geotechnical structure, foundation, pavement, earth retaining structure, etc. So a few studies are actually carried out to determine the physical, chemical, mineralogical properties of OB under static load condition. However, very few literature available on the dynamic properties of the material. So the objective of this research to investigate the dynamic properties of overburden material, then the evaluation of small strain shear modulus and the damping ratio subject to the range of strain, shear strain and confining pressure, compare with well-known geotechnical. So the Northern Coalfield Limited, NCL, Singrauli, is one of the few mines in the bordering area of Uttar Pradesh and Madhya Pradesh, two states of northern India. And you can see in this picture that the dump site of the OB material. these are the properties of the geotechnical properties of OB. So you can see that it falls in the, so if you see the parameter, so it is basically kind of a mixture of a small amount of gravel and sand in wide range, so it is classified as well-graded sand. So predominantly it composed of blasted sandstone with a minor presence of shale. So diverse range of sandstone and shale along with three seams. So the properties were examined, and you can see that large quantity of quartz. And so the ACM test confirms that the particle ranges from gravel size to fine sand. However, for the characterization, for the determination of the dynamic properties, we have used here the sand size particles. So we have sieved the material with 4.75 mm sieve, and this is the test which was conducted at NIT Silchar. So the resonant column apparatus with pre-fixed type of sample we have conducted. The sample size was 70 mm dia and 140 mm height. Relative density was maintained around 85% under confining pressure of 50, 100 and 150 kPa. The strain range was varied between 10 to the power minus 4% to 10 to the power minus 2%. So the sample was dry and undrained condition. Now, I'm not going to the details of the test procedure. So it's a basically a different range of frequency was actually excited, and the natural frequency was found out, and from there the shear modulus, dynamic shear modulus was calculated using these equations. And after that, the damping test was carried out. The load was applied in a torsional mode, and the damping ratio was determined through logarithmic decrement. So, coming to the results, so shear modulus is normalized with the maximum shear modulus obtained for the minimum strain level, and as we increase the shear strain with changing the voltage input, it was found that the G by G max curve is decreasing as expected. And on this figure, you can find out that with the increase in cell pressure, the decrease in G by G max is comparatively less with the fatter class. So coming to the damping ratio
Please
values.
wind up, sir.
So you can see that. So we have presented here in the normalized damping ratio, D minus D mean, and as the confining pressure is increasing, so the increase in the damping ratio is also decreasing. Now, if we compare with the other published results like Monterey sand, Ottawa sand, Kasai sand, Barak sand, published earlier. So it is coming within the range. So G max value is coming to be 27.14 megapascal at 50 kPa cell pressure, and increasing to 39.65 MPa at 150 kPa cell pressure. Similar range was obtained for other sand as well. And damping properties are D mean obtained was 0.8 at 50 kPa and decreased to 0.6 at 150 kPa cell pressure, and you can see that it is coming within the range between these previously published. Now, the shear modulus and the damping, it is highly strain dependent as usual, and confining pressure actually enhance the stiffness and decrease the damping properties. The dynamic properties of OB similar to well-known natural sand, suitable for geotechnical application under dynamic load. So it encourages basically the sustainable and eco-friendly reuse of mining waste. So insight into the sustainable geotechnical practices. So this is one of the practical
Please conclude,
applications.
sir.
Okay. So was carried out in IIT Delhi, and you can refer to these papers where other properties or other applications are actually there of OB material. These are the references.
Thank you very much. Any questions? Okay, thank you.
Thank you.
So now we move to the last presentation of this session. So the topic of the presentation is seismic response and instability analysis of moraine dam of Imja Glacier Lake. The authors are Biraj Ojha, Anchal Tiwari, Sandeep Sapkota, and Ramchandra Tiwari. Anchal, please stick to the time that is given to you. Please stick to the time that is allotted to you.
Good afternoon, everyone. It's me, Achal Tiwari from IOE Pulcher campus, Tribhuvan University, Kathmandu, Nepal. The title of my presentation is Seismic Response of Imja Lake Moraine Dam and Outage Structure under Kobe and Chile Earthquakes. So this is the structure of my presentation. Moving towards the background, seismic stability of moraine dams refers to the ability to withstand earthquake forces without excessive deformation, requires analysis of seismic response to ensure the dam remains stable during and after earthquakes. Stability is important to avoid sudden breaching and downstream flooding hazards. Outage structure in moraine dam regulate reservoir outflow and control water discharge in normal water flow condition. So this is my study area, Imja Lake Moraine Dam at 5,010 meter in Solukhumbu district, Nepal. And it is one of the 20 most potentially dangerous glacial lake in the Hindu Kush Himalayan region. So initially the lake area is nearly equal to 0.86 kilometers square according to Bajrachari et al. 2007, but it increased to 1.3 kilometers square according to Issimore 2016. Also, the maximum depth increased from 98 meter according to Bajrachari et al. 2007 to 116 meter according to Somos Valenzuela et al. 2014. That means moraine dam composed of unconsolidated debris with buried ice cores. Seismic stability is critical to prevent deformation, sliding, or glacial lake outburst flood gulf. Outage structure regulate reservoir outflow and mitigate downstream flood hazard. So geophysical studies were conducted for lake lowering and reducing the flood risk according to UNDP 2014. So this is my study area. Imja Lake growth slowed after 2000. Glacier retreat mainly occurs due to ice breaking of that is calving according to Fujita et al. 2009. And also lake expansion is driven by glacier retreat and meltwater inflow with discharge between 2.15 to 4.66 meter cube per second according to Thakuri et al. 2016. So this is the streamline pattern of the lakeside area. So the problem statement is the outage structure of Imja Lake Moraine Dam needs assessment for seismic stability and earthquake loading. The structural performance, that means including stress, displacement, and overall response under seismic forces is not fully understood. Determining the peak ground aspiration and structural response is essential to ensure safety and prevent potential dam failure. So the main objective of the study is to perform a seismic stability analysis of the outlet structure built on the end moraine dam of Imja Glacial Lake. The specific objectives are to perform the numerical modeling using finite element analysis to evaluate the structure behavior of the outlet structure under seismic loading, to determine the peak ground aspiration for earthquake of different magnitude, to determine the maximum stress, maximum displacement, and other structural response of the outlet structure under seismic loading. So moving towards the methodology, first is seismic response analysis of moraine dam and outlet structure. First, collecting reference for the possible underlying geometry of the moraine dam, two-dimensional module creation of moraine dam and outlet structure, collecting reference for the structural configuration of the outlet structure. After that, collecting reference for the preparation of material model for moraine dam and outlet structure, and conducting seismic stability analysis for both moraine dam model and outlet structure model, and also determining the governing parameter for seismic response analysis. So this is the ERT profile. From the ERT survey, 3 different types of soil surface were identified: frozen moraine, dead ice, and water-saturated moraine. So this is the extracted profile of moraine dam. This is the extracted borehole log data. So we perform 2D model creation. The analysis is done by using Plaxis 2D software. And the model parameter of Imja Lake include 2 types. That is 2-dimensional model of the Ind moraine dam, terminal 1, and 2-dimensional model of the outlet structure built within the moraine dam. And borehole logs extracted previously will be used for model creation. So the model of the moraine dam was created using bathymetric and topographic map of the lake, showing the longitudinal profile and cross-section along the deepest point from UNDP 2015. And the prepared model of the Ind moraine represents a cross-sectional view of the moraine dam, which is represented by AE1 line. So this is our 2D model of the moraine dam. This is our location of the moraine dam model. So we identify the actual location of the outlet structure using Google Earth, and we also perform georeferencing to select the ERT profile that best represent the site condition. So these are some of the geometrical parameters of the outlet structure. Here we use M25 concrete, Gavin work, GI seat pile, excavation, and sluice gate, and along with their dimensional description. This is the structure drawing of the outlet structure. So these are some of the soil parameters we have used based on different literatures. These are the concrete parameters. These are the sluice gate parameters based on different literature. These are the rock fill parameters. This is the backfill parameters. So moving towards the soil parameter for outlet structure surrounding the soil profile, this is the geological cross-section we interpret from the geoelectric station from UNDP 2014. So here we use the material model for modeling of structure element in outlet structure. For example, in case of M25 concrete work, material model is concrete material model. Region is, it captures the elastic and elastic behavior of concrete under stress. Representation is simulated using soil polygon to model the interaction with surrounding soil and structures. The second is Gavin wall, rock fill, material model, hardening soil model. Regions represent non-linear stress strain behavior and stiffness increase with depth, suitable for rock fill. The representation is soil polygons, simulate interaction with surrounding structures and environment. And there is wire mesh, the material model is plate element. Region capture tensile strength and stiffness of thin flexible wire mesh. Representation is plate element model, mesh rock fill interaction ensuring realistic Gavin wall behavior. Another is sluice gate, material model linear elastic, region suitable for metal like steel that primarily show elastic behavior under loading, and also soil polygons is the representation. So this is the soil model in the location of the outlet structure. These are the model after the installation of structure and 2D dimension of outlet structure. This is the meshed model of moraine dam and meshed model of the outlet structure. This is the stress construction for the moraine dam and stress construction for the outlet structure. Here accounts for change in soil conditions, stress and deformation. These are the time history record of Kobe and Chile earthquake. So due to Kobe earthquake...
Your time is up. You may have to conclude.
Okay, I will. Total displacement in the moraine dam of Kobe earthquake is 0.1955 meters, showing a distinct deformation response compared to other earthquake, and maximum displacement is 0.05971 meter, and displacement is considered along a contour line from the outlet structure with the largest movement at the backfill. In case of Chile earthquake, the maximum displacement is 0.19, outlet structure displacement 0.025, and displacement concentrated at key interface, that means backfill, Gavin wall, M25 concrete, water-saturated moraine, dead ice, and frozen moraine. So in case of Kobe earthquake, horizontal acceleration is 0.06, vertical 0.02, and overall maximum acceleration is 0.07 meter per second square at moraine dam. In case of outlet structure, horizontal 0.13 meter per second square, vertical 0.10 meter per second square, and overall 0.16 meter per second square. And the maximum acceleration occur at the base of the Gavin wall. That means decreasing towards the frozen moraine layer. And acceleration values indicate a strong seismic impact, higher than the Chile earthquake and comparable to the Gorkha earthquake. So in case of moraine dam in Chile earthquake, horizontal acceleration is 0.07 meter per second square, vertical 0.01, and overall is 0.07 meter per second square. In case of outlet, horizontal 0.05 meter per second square, vertical 0.03 meter per second square, and overall is 0.05 meter per second square. And lower acceleration indicate a milder seismic event compared to the Gorkha earthquake. Whereas in the midsection of the Gavin wall, mixed speed and strength. Okay. This is the stress analysis of the Kobe earthquake, effective minister 9.21 and maximum value 564. In case of outlet, 26.82 and 425.9. In case of Chile, 9.064 and 565.2 diametric stress. This is of outlet. This is strain analysis of Chile at outlet structure. Accretion versus time graph analysis of in-moraine and outlet. Displacement versus time graph. And validation, I have validated with the theoretical and historical performance of Gorkha earthquake 2015. This is the field scenario-based validation. So my conclusion is, the outlet structures showed maximum displacement of 0.025 in Chile and 0.05 in Kobe, indicating mild to moderate deformation, mainly in the Gavin wall, backfill, M25 concrete and moraine layer. The Kobe earthquake generated higher peak ground accretion, resulting in greater deformation. Both events produced similar effective mean stress, but diametric stress exceeded at key interface. Strain value were significantly higher during the Kobe event compared to that of Chile. Stronger sagging had greater structure impact, particularly in the Gavin wall and backfill zones. Repeated high stress zones were observed in water saturated moraine and near dead ice, highlighting the need for reinforced design to withstand long-term seismic effects. Due to limited field data, simulation results should be interpreted cautiously as they lack direct validation. And the 2016 lake lowering addresses the static case. However, dynamic earthquake protection measures still require further analysis and design. Thank you very much.
Thank you, Achal. Any questions on this, please? One question can be taken. Okay. Fine. Thank you. Thank you very much. So with this, we come to the conclusion of this technical session. Hand over to Chair.
Thank you. In this session, we have 10 presentations, and then majority of the presentations was focused on liquefaction potentials and cyclic degradation of the soil. Shweta presented cyclic behavior of cohesive soil. Mr. Sinha presented analytical framework on the excess pore water pressure estimation on two-layered system. Mr. Sophie presented interesting cases on cyclic response of Leh-Ladakh soil. Then the Achal presented seismic response of Moraine Dam and the outlet structures using Plaxis 2D. Nishimura-san presented effect of seepage and suction of cyclic response on saturated and unsaturated soil specimens. Sanjeev presented investigation case studies on liquefaction potentials using microtremor surveys. Mr. Alok Kumar has presented seismic behavior of zoned embankment dam using GeoStudio on one of the dams in Gujarat. Dhanya JS presented interesting case on ground vibration measurements using blasting. And then 2 chimney cases at Tata Steel was presented with some of the field instrumentation and field measurement has been carried out. The Kaushik Das has presented a cyclic response of coal overburden, and then it has been compared with standard geomaterials, and their liquefaction potentials have been compared. So with this, almost 10 presentation has been made on the field, or I would say the theme of earthquake and soil dynamics. With this, I will, let's say, close this session, and will hand over the session over to the organizer. Thank you.
Thank you, Dr. Jayakumar Shukla, Chairperson, and Engineer Anna Ponni, Co-Chairperson, for your esteemed presence. Now, requesting Dr. Anil Joseph, he will be giving a small token of appreciation, a memento, as a gesture of gratitude from the organizers. So thank you guys. This session is over. You can leave.